you get along all right working the problems? No?
No. Awful. Traumatic experience.
What's the trouble? What's the problem?
How do you figure out on the third problem what your y value is supposed to be? You gave the equation v times y over f times x.
Well, and the third problem, of course, is a one where you have to really have about three simultaneous, three equations and three unknowns about what it amounts to. The y and the x is simply you have to use a relationship. Y is equal to 10x, of course, along with the relationship that I gave you about the fraction, which represents percent recovery. It's very simple problem once you set it up correctly, but it looks like it's kind of perhaps at the first glance that you don't know enough to work the problem. Somewhat interesting when you finally work it out that the answer is independent of the actual composition of the feed. It'd be the same. The numerical value of x of f cancels out in solving the problem, so it's rather independent of that. As I recall. I forgot how the problem was stated. Yeah. Well, of course, you have to have some numerical value for the percent recovery from problem 2, which I got as to be about 90 or let's see, what did I get? 96.4 from the problem 2. And so you work it out.
I refuse to believe.
So the problem. So in problem 3, you basically use 3 relationships. One is the equilibrium relationship, y is equal to 10x. One is the relationship based on the mass fraction. In other words, y is equal to f minus 1 over f times x plus x of f over f, the standard process equation. And the third one is the relationship based on the recovery. Fundamentally, you've got y and x and f are unknowns, so you need 3 relationships. As it turns out, x of f is a constant, and in fact, the answer is independent of x of f. Does that answer your question?
So the B part of 2, what was the percentage part?
Percent recovery?
Yeah. Because I think I knew, one of us got a different interpretation of what was asked.
Well, problem 2 had to do with applying 2. It may be a rather hypothetical type of a problem, but it's a good exercise mathematically. And so, in other words, you have the first stage. You have the vapor going off, which I call V1, and this is the feed, of course. And liquid going off here, but this is introduced into a second stage, which, to keep it straight, we'll call V2 and then L2. And, of course, you'll have a Y1 and an X1 and a Y2 and an X2. And so the question was, what is the percentage of the volatile constituent recovered in the 2 vapor streams? Is that the way how it was? What is the overall percentage of the more volatile component recovered in the combined vapor streams from both stages?
What I did was I calculated how much of the volatile component was in the combined streams and not the percent recovered from the beginning. That's the way I interpreted it.
Yeah, so did I. You work out the
Because
percentage
it
coming
said,
out of the combined.
what is the overall percentage of the more volatile component recovered in the combined vapor streams from both stages?
Well, that'd be all right. That'd be all right. But you could mix these two after you get them out of the system. We're only concerned with this particular system right here at the present time. If you want to take these out and mix them, that's something subsequent to the problem.
That's what's stated in the question.
Well, all right, you can combine them then. But in other words, the percent of the volatile constituent, you can call it A if you want, or don't even need a designated percentage of the volatile component in question. And maybe there's of course, there's generally two volatile components, but we're talking about when we say the more volatile component, the one we generally treat as the more volatile. Recovered in the vapor streams would be what? It would be equal to V1, Y1, that'd be the amount recovered in the first stream off the first stage, plus V2, Y2, the amount recovered in the second stage, divided by the amount input, which is F times X sub F. That'd be all it is.
No.
What did you read?
I read it as the percentage of the volatile component in the vapor stream, the combined vapor streams. So I calculated the amount of volatile component in the two vapor streams over the total amount of vapor stream as a percentage.
You got 24% in the first one and about 6% in the second one. And then you work out the amount that comes out and put them in proportion to get the average concentration.
You get the same answer as this.
No.
Well, you don't get, of course, this is divided by the amount in the feed to get percentage, but well, if you interpret this, you interpret it to mean what is the concentration in the combined streams. Well, that's I'd answer that as a misinterpretation of the problem then, because it does say, as I read it here, the percentage of the more volatile components recovered in the combined vapor streams from both stages.
Yeah, it doesn't say anything about total overall recovery. It says how much of that volatile component is in that vapor stream.
How much is recovered in the vapor?
Okay, well, maybe I didn't express it clearly enough. I did say overall percentage recovery. I could have said, what is the overall recovery? But this is saying it just almost the same way. What's the percentage of the more volatile component recovered? And that's the same as asking for percent recovery. This to me. Well, maybe what you did is all right. I don't know if you didn't put in what you. Let me see what you got. Well, maybe I might ask what as a sample from problem 1, what percentage of what weight percentage of alcohol would be in the residual liquid and the vapor if you had a fraction vaporized was 0.5 or half. What answer did you get for that? This is for question. I'm asking question 1, just a sample answer here to see it. In other words, I ask what did you get as a concentration of alcohol in the both the liquid and the vapor streams for 50% volatilized or vaporized?
4.7 and 35.
Yeah, that's the same. Yours not right. The one answer I just heard, yours is about right, yeah.
4.735?
I got it on the phone last night.
You want to do it the same way?
I got 5.0 and 35.0. Huh? Yeah.
4.7.
Well, one might get a little variation the way you draw the curve with the number of points you plot. All right. Well, all right. We'll have a look at them. Unless you have some more questions. Another question?
Did you work out that percent of all components? I don't understand where those numbers actually come from, all those numbers.
You don't understand why this is a...
No, I can understand that, but could you go through maybe problem 2 once, just real quick? Like working it out, actually.
Well, that's what you're supposed to do. Of course, this is... Well, let me take a hypothetical case. I'm going to take the answer in a particular problem. Suppose you had where you take the feed as a basis, or 1 or 100, whatever you want, and let's say, for example, the fraction vaporized in the first stage was 0.25, so V2 would be, V1 would be 0.25 F, or 1. And let's say Y1 was, let's say, well, Y1 would be something greater than X sub F, so let's take it as 0.2% or something. No, let's take it about 0.3 or something, maybe more than that. 50%. Then V2 would be equal to the fraction vaporized. If this is going to be, is V1 is 0.25 times F, and down, and of course the liquid would be 0.75 F. So in other words, in this particular case, then V2 would be 0.75 times fraction vaporized, which in your case was 35. So whatever that answer is, I forgot now numerically. And let's say that Y2 is something like 0.08. I don't know whether these are even close values or not. But and so if that was now these would be mass fraction, of course. So if these were the answers, which they aren't for the problem, well, you simply would put in here then that you'd have 0.25 times 0.50 plus 0.75 times 0.35, whatever that numerical answer is, times the concentration 0.08. And this is divided by the feed, which you take as 1 times X sub F, which I guess was 0.80, but in that particular case. But these aren't necessarily the right answers. Those are not the quite correct values for the concentration. But that's the way you do it.
I was more interested in like the vapor off the second phase of that. You get the feed in. Okay, you start out with 1, you take 25% of that vaporized, right? In the first phase?
No.
This is the actual problem.
Yeah. 25% of this feed goes off as vapor. 25. For each 100 pounds you put in here, 25 pounds of vapor goes off.
Okay, so then that means 75% of it goes down the bottom.
Right.
Okay, so 0.06 is the feed. And then in the second phase, 35% of that is vaporized. So you take 35% of 0.06?
Well, in order to get the amount vaporized, you take 35% of 75F, 0.75F.
Volume, not concentration.
If you want to take the base as 100 pounds, that's a pretty good figure. Then you don't worry about fractions if you like. You have 75 pounds here. 35% of that is vaporized, so it's 0.35 times 75. I don't know what that is. It'd be about. I probably got the answer here somewhere. I forgot what it is, but 3. Be about 26 pounds, and then it would go in the second vapor. 264, whatever it was. Well, now, I had begun to initiate discussion about the continuous fractional distillation. Do you have another question?
I want to know the answer to the last problem. I don't know if you said that. Third one?
Numerical answer?
Yeah.
What'd you get?
Well, as a mass fraction, I got, or as, F, I got 0.48.
Now, the last question I was asked, what would be the fraction vaporized? And what'd you get?
I got 0.48.
What percent recovery did you get from problem 2?
Well, I did it like I told you before. I got 15%, but that's volatile component in the total vapor stream. And I use that figure to calculate.
I can't compare my answers with yours because I worked at the. I got 96 point.
What'd you get for the fraction vaporized?
So I got about 0.627. Is that what you got?
Yeah, it should come out the
It
same.
should come out the same.
Okay. Well, now I'd like to discuss or continue our discussion about some of the fundamental principles of the multi-stage continuous distillation, or what we call continuous fractional distillation or rectification. And I had rather qualitatively or indicated how you can utilize the vapor-liquid equilibrium curve to visualize how you can go from one concentration to another by repeated steps, particularly if we can consider the system under equilibrium, which in practice is only by taking the steps between the curve and the diagonal line. In practice, this is only approached when you have a system under balance on a total reflux, or in other words, no feed or product removal. So in other words, this has to be modified in order to represent practical conditions. So let me start out today by saying that I'll take 2 or 3 periods to discuss a quantitative treatment of continuous distillation, and it will be from the standpoint of proceeding to the elements of design of a column to perform a particular stated set of specifications for product and feed material. And I hasten to point out that it's not our objective to make you design engineers, but even in an elementary sense. But once we go through this procedure, I think it'll then be clearer what happens, how you can understand what's happening when it's applied to a definite case let's say, an existing column, and you try and interpret what maybe goes on, or how it deviates from what would be considered the optimum utilization of it from the design standpoint. So the purpose is to maybe to comprehend the principles and functioning principles sufficient to permit intelligent understanding of operation and troubleshooting, if necessary, of abnormal behavior. Now then, there are about 3 or 4 sets of parameters that we can consider in determining what the requirements would be for a piece of equipment to produce a given set of separation. And the first is the number of stages. That's a rather obvious requirement. The number of first of all, the number of stages. This word stages we refer to as a stage of vaporization, or you can think of it as plates or trays. In actual design.
How would you state that if you're using a packed column?
Well, in terms of packed columns, that's another thing I was coming to. We still calculate the number of ideal stages, and the usual treatment is to estimate the height equivalent to a theoretical plate of a packing. And so you still simply divide by if you're you still have to figure out the number of ideal trays, and then if you have some knowledge of what the height of a packing is equal to one theoretical tray, well then you have that much height, of course, or have to have that much size. Mm-hmm. Well, anyway, now the number of stages is the parameter which establishes the degree of separation of components attainable, especially if we specify a given reflux ratio.
Repeat that.
Or, well, I say the number of stages is the parameter which establishes the degree of separation possible for a given set of specifications of feed and operating conditions, particularly the reflux ratio. And or you might say it this way: is that the number of equilibrium or ideal stages that's required depends on the degree of separation specified. That is, the specifications of the products, top and bottom, and the thermodynamic behavior, the vapor-liquid equilibrium relationships of the components in question. Of course, that has to be come into it. Then secondly is column sizing. For example, the height and the diameter. As I'll put down here, degree of separation is primary consideration here in the number of trays. Column sizing here is primarily concerned with the loading, the load, or the throughput, or the how much you're going to produce. Has to do with the with the loading or quantity of product. Of course, the number of the height here is directly related to the number of trays that you get here first, and whatever spacing between the trays is decided upon, which is another consideration to be looked into. And the diameter, of course, is directly related to the throughput for a given vapor velocity. You have to the required cross-sectional diameter is directly related to the load, the amount of the vapor load. So naturally, for a bigger distillation quantity, well, you have to have a bigger diameter. Not necessarily a bigger height, but it's going to be a bigger diameter.
What does the height depend upon now?
Well, the height depends upon, of course, the number of trays. In other words, if you have to have 50 trays, why, it's going to be essentially 5 times as much if you only had 10 trays, everything else being equal.
Is there some relationship between how far apart the trays are and the increasing diameter of the base?
Well, there's the height and diameter are sort of interrelated, along with plate spacing, as far as the plate spacing determines the height, because you can, and we'll come to this later, you can, by having larger plate spacings, tolerate larger vapor velocities, and therefore have a lesser diameter for the same vapor velocity. If you have close plate spacings, but then the factors are that you have a more limited allowable vapor velocity, because then entrainment it becomes more significant. The word entrainment, I'm getting probably ahead of myself, refers to the physical carrying forward of liquid droplets in the vapor. So in other words, if you have too close a plate spacing, the bubbling action will carry a significant amount of the liquid droplets, up to the next stage, and therefore defeat the purpose of it, defeat the purpose of fractional distillation. In other words, you're trying to establish a gradient of concentration as you go from stage to stage. If you mechanically carry up liquid from one tray to the next, you're defeating the objective, because you're tending to blend or mix two streams, and the purpose is to separate as far as concentration is concerned. So this is what determines, one of the aspects of determining plate spacing, is that which will enable you to have acceptable level of entrainment. There's always a little bit goes on. And therefore, if you have a larger plate spacing, you have a higher vapor velocity without getting significant entrainment. As a matter of fact, really properly designed design for a given separation requirement, an engineering firm would, when they get to the subject of height and diameter, they'd work a number of problems, a number of probably assumed situations. Assume one plate spacing, and calculate the proper diameter and height, and then determine the cost of the equipment. And then they'd take another situation where they'd have a closer plate spacing and maybe a larger diameter, and calculate it again and calculate the costs. And do this and maybe plot a little curve of height versus diameter, and then take the place where the cost versus, well, plot cost versus one of the parameters and find where it passes through a minimum. This is the way engineers do, try to determine the optimum. And so they're interrelated. Now, there's several sort of other factors that enter into this, and this is related to the industry concerned. Now, several years ago, quite a few years ago, the plate spacings used in the alcohol industries was much shorter, much smaller than used in petroleum or chemical industries. Particularly dictated by the fact that the government regulations, the legal requirements required that they be housed in a secure building to protect the revenue. And so the problem then of housing a distilling column inside a building and the cost of the building related to it, of course, was a very important factor in height. So then they would tend to dictate having small height as possible in order to cut down the cost of the building. This particular aspect resulted particularly also in the practices I'll talk about in a later period of splitting the column into sections and putting it into two pieces down on the floor. In other words, you can take a distilling column, which fundamentally consists of a concentrating section above the feed and the stripping section below the feed, as we already know, and you can make it in one single column. But you can cut it in two at any particular point, preferably near the feed point, and put the sections down beside each other, and so have about half the height up to the top. Of course, if you split the columns, now we do call that a split column arrangement, where it's simply the distilling unit only consists of a stripping column and a concentrating section, or concentrating column. Naturally, you have to make some provision for connecting the vapor from the top of the stripping section to the bottom of the rectifying section. Maybe I might as well indicate what I'm talking about by a little sketch. And they also have to make provisions for pumping the liquid overflow from the bottom of the concentrating section back to the stripping section. In other words, if a single column in its simple form would be something like this, where the feed goes in here, and we call this a stripping section. And the upper part here, the concentrating section. And of course, you know that, or can visualize, I think, that right here at the feed tray, there is, of course, liquid overflowing down to the next tray, and there's vapor rising, passing up to the tray above. But at the same time, if there's any functioning, there's liquid overflowing from this tray and vapor passing on up. So if we're going to separate these two sections in order to save height, we've got to make some provision for conducting the vapor from this tray, or wherever we split it, to the bottom of on over to the bottom of this, to the bottom tray or the bottom part of this section, and have some provision for the liquid to return back to the stripping section. So in other words, a very rather common design, let's draw this a little bigger, is to put the two alongside each other. And so here we'd have the feed up near the top. It might be actually split, not right at this point, but at about here, 2 or 3 trays above sometimes they put on above the feed point, but it can be exactly right at the top. So this is the stripping section, with, of course, the feed going in here, and steam, if it's direct steam heating. in here, and now then, we don't have any condenser here, but we actually bring a vapor stream down to the bottom here. And so we have a big long vapor pipe. This in itself is a little bit of a disadvantage, but we are saving the much in height here, you see. And so we have trays in here, and of course you'd have up here you'd have one or more condensers. And a certain amount run back as reflux in its simplest form. This would be the concentrating section. And so then you see the vapor comes in, you have to have the vapor being conducted into this section. Now we also, the overflow from this tray is going to produce a liquid phase down here, which first has got a considerable amount of alcohol in it. It's in the middle of the column. And so you can't destroy, you can't throw it away. In fact, you've got to provide a pump here and pump the liquid back to the top of this section here. So this would be the reflux pump or reflux return. So this is what we call a split column arrangement. But it's still about the most simple type of a continuous distilling unit in that there's only a stripping section and concentrating section. Yeah.
Well, why isn't the second part of the column heated? I mean, if you heat it, wouldn't it? Yeah. Why?
If you apply, there are types of units where you apply heat to the second column, but then you become truly a second additional column type arrangement. I can draw you several sketches here of a type where, well, I'll draw you one just to distinguish from the fact that suppose you had like they do in the grain distilling industry in the United States. They usually have what they call a beer still. And it simply has, it may have 3 or 4 concentrating plates on the top here, but that's about all. But primarily it's perforated plate column, which is intended to recover the alcohol out of the beer. Beer is a term for fermented grain mashes. But anyway, this would be the feed. Now then, this vapor going off here is condensed. Usually there's about 2 or 3 of these condensers. The first one of which is usually a preheater. And so I'll just draw in here 3 of them for. And then finally you'd have the distillate here, the distillate here, and this would be a vent. Anyway, this would be a beer preheater. But anyway, they all provide either reflux, or the condensate is either reflux, or it may be arranged in such a way that you can take off some of it as product. But anyway, the product then of this would be called low wines. They use the word wines in the grain distilling industry. I don't know what they call low wines or high wines. But anyway, one or the other. I think sometimes they call it high wines. As a matter of fact, and getting off the tangent somewhat here from what I intended to cover this morning, we're in the first step in producing what they call let me see, what did they call it? They don't, at this stage they don't call it bourbon, but it would be what I would call bourbon distillate. I think they just call it high wines. That's what they term it, and before it's processed and becomes legally bourbon in the industry. They don't call it bourbon. But anyway, fundamentally, this material here is the basis material for bourbon. Then they run it through what they call a doubler, or sort of a continuous pot still, you might call it, a big, large place where they vaporize it one more stage. In other words, this might go into a large pot still, where it's not really, where they have a continuous, where they have a steam coil here, and this is re-vaporized and condensed, and this is whiskey distillate. And the proof is limited to 160 proof or less. Anyway, that's about the way they do it. They barely get it up to 150 or 60, 160 proof. Make one vaporization here in a big pot still. Either continuously or periodically, this liquid retaining here be recycled back into the system somewhere. It can be operated sort of batch-wise. And many do run it batch-wise, but it can be sort of made on a continuous basis. So this is running in continuously, some going out here. So if this is kept level here, and well, this just represents one more big plate, doesn't it? One more stage of vaporization is what it amounts to. So if you wanted 160 proof here, you'd probably run it in here at about 120, something like that, maybe 100 proof. But what I started to write here was would be that instead of running it into this sort of thing, you could take this. I'll erase this now. You can run this into, a plain rectifying column. This liquid here, which probably go into what we call a low wines tank or accumulator or a high wines tank. Would then be fed into another column. And so now we have to have heat supply to this column because we're going to feed a liquid in here. So now I have to have either steam, direct steam, or a reboiler at the base. And of course, this could be this could constitute the rest of a process to make, let's say, relatively high-proof spirits. Not the cleanest high-proof spirits, but you could use a system like this, where now you've got a beer still over here, which essentially consists of a stripping section, maybe a very short concentrating section. But now you introduce this into another column, and so now you have a stripping section here and a concentrating section here.
What's the advantage of that? Why don't they just run the beer still directly into the column?
Well, there's various reasons, and it's a little too complicated to answer your question right now. I'm not sure. So this would be called a double column unit. I would call it, not a split column, but a double column unit, because these two are two separate distilling columns. Whereas over here they're really only split in two for convenience. As a matter of fact, you could use this second column here as the way I've drawn it here now. This, if you took off, let's say, high-proof alcohol up here somewhere, this would be sort of a conventional concentrating section, and the residue here would be waste or discharged to the sewer, essentially be water. And you'd probably take some heads off of there. So this would be fairly simple type of a arrangement to make grain spirits. Another arrangement would be that to use this column here. hesitate to draw a lot of diagrams here now, would be to have a third column here, but utilizing the middle one is in a different basis, different way. If we run this low wines into this one here and operate in such a way that we take off heads here, but don't take off only a small amount here, and take off the main product down at the bottom here, let most of the alcohol come out here as a low-proof alcohol. Well, we have what's been called in this case a purifying column. Now this low-proof alcohol then would be fed into the middle part of this final column, which would be a concentrating column, the concentrating section. And of course it'd have its condensers up here, and you might have a small heads cut taken off here, and you might take the product off as a side stream a few trays down from the top, the spirit. But anyway, and this would of course have to have a steam also, either direct heating or reboiler. So this would be the way I've drawn it now. You'd have a 3-column unit. This would be 1, 2, and 3. This would be the rectifying or the concentrating column. But the way it's set up here, it has a even though it's called the concentrating column, it has a concentrating section and a stripping section.
Wait.
So I've gone here a little beyond what my intent was. I've given you 3 or 4 different designs of multi-column units. I really only was intended to talk about a split column.
Is this for speed that they would do something like this?
No.
Why not just save this chunk off the bottom and put it back in the same one?
Well, there are various reasons for doing these. As a matter of fact, it's primarily associated with getting the desired purity of spirits that they're after.
Oh.
The advantage of having a purifying column in between here, in order to remove the more volatile components, is related to the fact that these more volatile components, including acetaldehyde and ethyl acetate, are much more volatile from weakly alcohol solutions than they are from high alcohol solutions. So you get a more effective separation by making the separation at low-proof alcohol than you do at high-proof alcohol. In the wine industry, they use, and here in California, they frequently use 3 columns in the sense that they have this to start with, although they may only just use it this way. But anyway, they'll have another 3rd column out here that they call an aldehyde column, in which they take the product that's been made without a complete head separation and run it through another column at full proof, at high proof, to remove the aldehydes. Well, it can be done. It works okay, but it's not quite as effective a separation as you'd get by running it through a low-proof column first. In other words, you can reverse a principle, these two, reverse the order, so to speak. And as a matter of fact, when you get into making very neutral spirits, well, they may use 5 or 6 or as many as 7 columns in a particular unit. Every one has some particular function. For example, if you want to make the most complete separation of volatile components, they sometimes run the low wines here into what they call an extractive distillation column. Instead of calling it a purifying column, they run the liquid into a column like that, but up to the top of the column they'll add hot water so that it'll keep the proof very low, down to the order of maybe 5 or 10 proof maximum in the column. Under those conditions, not only does the low boiling constituents go over in the top stream, but also the high boilers. The fusel oil components and the esters, fatty acid esters, they distill over in the heads. And so then the very dilute effluent out the bottom then is concentrated in one or more columns after that.
How does it use both high boiling and the low boiling volatile components at the same time?
Well, of course, the low boiling components like acetaldehyde and ethyl acetate are more volatile than ethyl alcohol or water in any proportion. That is, they're always more volatile. As I explained before, the components that are the high boilers that have limited solubility in water have volatility greater than 1 only in rather dilute alcohol solutions or water. And so by getting the dilution low enough, by adding water to the column, so-called extractive distillation principle, you can cause almost all organic flavor materials or contaminating materials, if you want to look at them that way, can be made more volatile than ethyl alcohol. Remember that chart I gave you, where if you get them low enough, they cross over the alcohol curve, a volatility chart. Question?
If something's more necessary if you use like pumice for your distilling spirits and things like that, then you just use wine. They use the same distills for either one.
Well, why don't you postpone that question about pumice till we get a little more time. Let me, I know the time's up, but let me just put down what here, two more things here just to complete this outline. Now we could discuss column internals. In other words, the type, bubble caps or trays, what to use. You can have, for example, the trays can be bubble cap, or more popular now, a variation of that called valve trays. Or they can be perforated or sieve trays, very commonly used in the stripping section, or not very much practical use in the industry. That'd be pack columns. And a fourth set of parameters that we could practical engineers would be concerned with would be the accessories, such as the condensers and the feed pumps and the heat reboiler and things like that, and instrumentation and all those things that I consider accessories. And so these are kind of an outline of things that one has to consider. Well, let's see. I was going to give you a handout here and discuss the functioning of a bubble cap, but I didn't get it handed out. But I'll give you the handout anyway. And